what we said was when in certain situations, whether n is large, p is small, or n p greater than 5, n q greater than 5, a discrete distribution also starts looking like a continuous distribution. But there is something about that shift from discrete to continuity that has to be addressed. And that's where we will get started with continuity correction. So let's say we are all playing Who Wants to Win a 5-Star, and so what's the probability you will get 5 or fewer correct answers out of 12, given that each question has only 2 possible answers? What kind of a distribution is that? Binomial. 12 number of questions, the number of trials fixed, only 2 outcomes, and independent. Whether you answer one correctly doesn't depend on whether the other is correct or not. So 5 or fewer. So how do we get the binomial probability? CR, p to the power of r, q to the power of n minus r. N is 12. P is r. 2 possible answers, so probability of answering this or that way, 50-50. So P is R. So Q is more. R, 5 or fewer. So 0, 1, 2, 3, 4, 5. You will have a cumulative distribution. Basically, cumulative probability is what you have to calculate. For 0, 1, 2, 3, 4, and 5. So 5 or fewer. So let's do that. And the notation, just get used to that. Random variable x, and the random variable here is the number of correct answers, or number of correct answers, is distributed as binomial 12.5, NP, binomial NP, and we need to find x less than or equal to 5 or x less than 6. Okay, and we do that. 38.7%. Now, can we approximate it to a normal distribution? The rule for binomial almost approximating normal is NP greater than 5 and NQ greater than 5. That was the last slide we covered yesterday. The last one was Poisson. Poisson lambda is more than 15. We consider it as normal. Binomial NP is more than 5 and Q is also more than 5. NP 12 times 0.56. Q is also 0.5, so 12 times 0.56. NP is equal to 6 and Q is also 6. So it meets that requirement. So I can approximate it. If I can approximate it, then a normal distribution, what does it mean? Mean and variance. See, geometric distribution needs the probability of success. Binomial needs n and the probability of success. Poisson needs average number of events, lambda. Exponential needs average number of events, lambda. Like that, every distribution requires something. Normal needs mean and variance. Now, you are approximating it to normal. How do I get my mean and variance for normal? Because I need to know that. Expectation of a binomial. See, it is a binomial distribution. If it is looking similar to normal, whatever is the mean for binomial is going to be the mean for normal. Otherwise, it doesn't approximate. So, binomial mean is NP, expectation. NP. So, the mean would be 6. Now, I need normal, also needs the variance. How do I get the variance? NPQ, binomial variance is NPQ. See, just the calculation may all be different, but if the distribution looks the same, if I don't tell you what it is, if it looks nice symmetric, then you will say normal. And then I would tell you, no, this was a binomial. How does it matter? The mean doesn't shift. If it looks exactly the same, if it doesn't, then of course it is different. But if it looks exactly the same, mean and variance of a binomial will be the mean and variance in the normal situation as well. I'm approximating, but they are looking the same. Okay? So variance is NPQ then. N 12 times 0.5 times 0.5. So 6 3. So normal 6 3. That's what it is. Okay. Suppose I had a Poisson, and the average number of events for Poisson is given as 10. Let's say no, lambda more than 15 is what I'm saying, it's approximating normal. So let's say lambda is equal to 20. Can I approximate it to normal? Yes. If I approximate it to normal, normal needs mean and variance. What would the normal? Lambda. The mean and variance of a Poisson is lambda. So normal would become 20, normal 20, 20. That's it. Nothing fancy here. Okay. As long as you know the expectation variance of each distribution, and if it looks similar to another one, same value. Okay. So now I want to get, that's what I'm interested in, less than or equal to 5, which is less than 6. Answer is correct out of 12. If I have to get that same probability using the normal distribution, in binomial we calculate 38.7. Exact probability. No question of approximation. That's the perfect answer. But I'm saying I can approximate it to normal. Now, so I should be able to calculate the probability, and it should be the same. Similar. Close. How do I get p less than 6? Probability of x less than 6 in normal. What's the first step I do? Z-score. Perfect. I mean, just take the chocolates. I heard many people. In normal distribution, if I ever ask you a question, what do? You don't listen to my question, you just say Z-score blindly and you will be right. Okay? In normal distribution, I can't do anything more than that. I can standardize and I can calculate probabilities. Using R, I don't even need to standardize. Standardization as a method you need to know for many things. So it is good to know that. But R, you will just type the actual values also, actual mean, actual variance, and reduce the probability. So here I calculate the Z-score. What is the Z-score for here? How do I standardize anything? With this you have to know. Whether you use it in normal probability calculation or not, you better know what standardization is. X minus mu divided by sigma. Okay, you are giving me answers, but I want you everyone to know for sure how you standardize something. And what is standardization is calculating a z-score. What is a z-score? X minus mu divided by sigma. That means z sigma is equal to x minus mu. That means how far is x away from mean? X minus mu is how far is x away from the mean. Difference between the value that you are interested in and the mean. How far? Z standard deviations. Z sigma. That's what you are saying. If x is, in Julie's case, if x was 75.5 and mean is 71 and standard deviation is 4.5, so 75.5 minus 71, 4.5. Whoever was 75.5 inches tall was 4.5 inches taller than mean. How many standard deviations? One standard deviation, because you divide by 4.5, which was the standard deviation. Okay, you need to know z-score, meaning of z-score. Formula also, there is nothing in that formula. So if I do that, okay, you were giving me some answers. How do I get that answer? X equal to y 5. I am writing x less than 6. That's what I did here. X less than 6. X equal to 6. Okay, so if x equal to 6, 6 minus 6 divided 6 minus 6 divided by square root of 3. This is variance. Z-score requires standard deviation. But anyway, 6 minus 6, 0. If z score is 0, what is the probability P norm left of that? Huh? 50%. Z score mean is right in the center of the distribution. It divides the total data into halves. 50% data to the left of mean, 50% to the right of mean. That's what it means. That's what it means, the mean. Okay. Okay. So, or if you are interested, you don't know what to do with that thing, you look up the Z table. Z score of 0, 50%. 50% area to the left. Okay? That's interesting because when we did binomial, we got x less than 6, 38.7%. When we did normal, we get 50%. Is that a good approximation? No, by no chance that is any good approximation. Where is 38.7? Where is 50%? Too much. Okay? So, why that is happening now? That's where the continuity correction problem is happening. What is happening when I am using the binomial distribution to calculate the probabilities? I calculated x equal to 0, x equal to 1, correct answers, number of correct answers, the probability of getting 0 correct answers, plus 1 correct answer, plus 2 correct answer, 3, 4, 5. That's what we did. Isn't it? Yes.
So what exactly should be writing as x b minus 1 from 0.5?
Yeah.
X belongs to b. What exactly?
The random variable x is distributed as binomial 12, 1.5. Binomial needs the number of trials and the probability of success. And the question that I asked was very quickly. Yeah, you are playing this game, so you missed that part of the question. You are playing Who Wants to Win a 5-star. What is the probability you will get 5 or fewer correct answers out of 12 questions? That's a binomial distribution. 12 is the number of trials. Each question has only 2 possible choices, so 50% probability. Okay. So that is what it is. And because NP is getting more than 5 and NQ is also more than 5, I can approximate it to normal distribution with a mean of NP and variance of NPQ. So now, in binomial, when I got the probability, I got the probability of getting 0 correct answers, 1, 2, 3, 4, 5. I added all of them up. That is what 38.7% is. This value is the sum of all of these 0.16 plus 0.1 plus 0.04 or 0.42 plus something, all of that combined makes it 38.7. Now, when I am getting a normal distribution, the same x equal to x less than 6. In normal distribution, equal sign has no meaning. We saw that probability at a particular point is always 0. So, whether you say x less than or equal to 6 or less than 6, it's the same thing. Okay. So, when I am doing less than 6, what happens is, in normal, it's a continuous curve. You see? So, it adds this much part of the probability also to this whole thing. Binomial was adding only up to this much. Only this much. Normal adds this part also. I have to correct for that. So, what really is happening is, when I am using a normal distribution, you remember again your analog to digital conversion. When I said 5, I am anywhere for 4.51 to 5.49, I am rounding it off to 5 in a discrete situation. 4.51 to 5.49, I am taking all of that as 5. But in normal, I don't. I continue. So, what is this point actually in a normal situation? 5.5. This is 5.5. If I use x less than 5.5, then I am exactly approximating to binomial. 5.5 to 6 part. In binomial, I'm not taking that. I'm only taking up to 5.5. I mean, number of correct answers, there is nothing for 5.5, but 5 means 4.5 to 5.5. I'm calculating the overall area anyway. Don't worry about this. I couldn't draw this in Excel or something. All I'm seeking is just the peak. So, what I'm getting really is this entire area. So, this entire area in binomial, I'm getting this much area. And in normal, I'm getting this additional area. I just have to subtract that. If I take less than 5.5, I'm taking this entire area. I'm taking this entire area. That's what I'm exactly approximating binomial. If I correct for that half, and always be a half. Whatever type of problem, the continuity correction is always just half. Okay. And I'll ask you many questions after a couple of slides where you will become perfect with the continuity correction. So this is what I have to correct for. See, this is what it was. So that was what it was, and in normal, so this is normal and this is binomial. I'm just taking that additional part. Okay. So now if I use 5.5 minus 6 divided by square root of 3 gives me minus 0.29. Minus 0.2 here and 9 here. 0.3859. Now 0.3859 or 0.386, 0.387. Now that makes sense. That's perfect approximation. Agreed? Yeah. Okay, so let's see if you really agreed or not. Okay? Many questions. Historical data shows me in the class when I asked this, the first few things we are very slow. I think at somewhere around this point or some, we become speed. You become speed. Okay, I have not started asking. And all the others, the first day I just told you, watch who is jumping the gun and who is answering correctly and who is doing fast. Grab them later on, even if you don't understand now. Just grab them, they will explain. And if they are unable to explain, then you will post questions with the answer. So ensure you watch. If you are not understanding, first of all, ask, stop me. But if you are shy, watch your friends. So x is less than 3 is the discrete thing. In a continuous thing, if I have to do that continuity correction, what should x be? 2.5. Less than 2.5. That's what you also said. Anybody else? Any other ideas? How many agree? Okay, I'll come back to my standard way of asking. How many agree to 2.5? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And all the others, I am assuming that we don't know what's going on. A fair enough assumption? Because otherwise you will have some other answer in mind. Any other answers in mind? Let's not random guess, okay? Either it's 2.5 or we don't know what's going on. Good. Okay. So the way I try to remember, and because I'm a bit slow, I don't get things very fast in my head. So x is less than 3. So I go back to my previous thing here. Here, less than 3 means 0, 1 and 2 are included. 3 is not included. Close visualize. I close my eyes also to be able to visualize that. So 0, 1 and 2 are included. 3 is not included because it's less than 3. I'm talking about less than 3. If 3 is included, 0, 1 and 2. Less than 3 means 2 is included as the last one. 2 goes from 1.5 to 2.5. So x less than 2.5 is the right answer. Okay. I try to think what is the, depending on the sign, if it is less than something, then I see what is the last bar included in the discrete probability. And that bar, where does it end? If I am asking x greater than something, I say, what is the first bar included and where does it start? So that I include all the probability related to that. Go forward, back to where? Not here. Hmm. Yeah. Less than 6. Less than 6. So, less than 6 means it ends at 5.5. No? Less than 6, if I normally take, then it's less than 6 only. In normal, it is 6 only. No? Less than 6 means up to here. That part. That's why I should not include that. I have to correct for that, is what I'm saying. That is what I'm saying, is including in the normal thing. I should not include, is what I'm saying. I'm trying to draw it. I had to play with the things, and I may have to do a better job than this. This is what is included. Maybe I should, this part I should adjust the edges and move it down or whatever. But you get the idea. This is the additional part. Actually, don't see the previous one. This is the right thing. So this is the right thing. In normal, I am including this much of area also. In binomial, I am not. I am correcting for that. Yes. Yeah, so discrete goes up to 5.5. Anything in a discrete situation, anything will be up to 5.5. In this question, if you are getting confused based on the question that I can answer only 5 questions, then in continuous, what will you do with that? Continuous, if you say 5 in continuous directly means up to this point. You are missing that other part of it. Okay. So, what is depicted as 5? Don't go by the particular question. In a discrete situation, we round off things basically. So, up to 5.5 is considered 5. And the answer is right there anyway. The proof is there. Okay. So, less than 2.5. X greater than 3. Greater than 3.5. Greater than 2.5, who said that? The first one to say that. I think it's a correct answer. I don't know. If it is not, please still take the chocolate. Anybody thinking? I don't know. I have to think because I have not yet closed my eyes, so I don't know what the correct answer is. This was this confusion matrix thing. It just got me. Once we were doing a short program for BVRIT Girls College, and confusion matrix and all those things we taught them, and then I had conducted a viva for them, and I was asking about all the confusion, false positives, false negatives, and precision recall, and every single girl rattled off the answer like that, and I was saying, hold on, just let me close my eyes and think if that is the correct answer, because I couldn't think, and they were rattling off, and then after some time I said, yeah, that's a correct answer. Everyone did that. I said, never happens. I mean, nobody answers like that. That's when I realized they might have, I don't know, maybe they understood the whole thing, but they might have memorized the predicted and the actuals and all those things. So that since then I started mixing mixing them up. Okay, so that's the same thing. I still not close my eyes. So x greater than 5, I got an answer of 3.5. I got an answer of 2.5. And obviously there is going to be an answer of 2. I still don't have to know what's going on. So fair enough. So x now again x greater than 3. Greater than 3 means the first bar in discrete that is included is 4. Everyone agrees to that? Okay. And I am looking at the probability, the area to the right side now, greater than. So 4 means it starts at 3.5. So I have to start covering the area under the curve from 3.5. Okay? Sorry, so the chocolate goes here. See, I had not closed my eyes. See? So don't go by my chocolates also. Next time if I give a chocolate and they say, oh yeah, this is the answer, and if I next ask who agrees with that answer, and everyone raises a hand. See, I make mistakes. 3.5. Good. Next. X less than or equal to 3. 3.5, 2.5. Now I'm 3. Okay. So 2.5. Okay. So 3 answers are there. Let's now have a show of hands. How many? I don't even know what that is. Okay. So how many 2.5s? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 10 or so. How many 2.5 then 3? How many 3s? Wow. This looks like majority. How many 3.5s? Okay, this seems to be the minority. Let me put some these. X less than or equal to 3, which means 3 is included. 3 is included. 3 goes up to 3.5. The minority was the best. 3.5 is what is it? Yeah. Less than or equal to 3. So 3 is included. You have to decide what is included. If you just say x is equal to 3, x is equal to 3 in a discrete is what? It's going only up to 3 is going only up to 2.5. Okay? X less than or equal to 3. That means 3 is included. 3 ends at 3.5. Okay? Getting a feel for it? Equal to has no meaning in continuous. So whether you write or not, it doesn't. Okay, so 3.5. Okay, good. X greater than or equal to 3. 2.5. Yeah, x greater than 2.5 is one answer. More than 2.5, okay, another answer. Huh? And I still have no clue is another answer. I'm trying to read places. Okay. X more than greater. Okay. So my hand is there. Greater than or equal to 3. That means 3 is included. 3 starts at 2.5. 2.5 to 3.5. So 2.5. 2.5. Okay. Now, x is greater than or equal to 3 and less than 10. Okay, now the volume has increased and the answers are coming more rapidly. Still, some okay, whatever. That's agree. So 3 is included, which means it starts at 2.5. And 9 is included as the last one. Less than 10 means 9 is the last one. 9 ends at 9.5. So 2.5 to 9.5. Right, makes sense. Good. Who said that? Who said minus 0.5 to 0.5? I still don't know the answer. I just got a different answer. X is equal to 0. Just think of the 0 bar. It goes from minus 0.5 to plus 0.5. Isn't it? Isn't it? 0 bar most of the time people, even when they speed up, this is where the break happens. So, okay, I have the axis here. 0, x is equal to 0. 0 is here. The 0 bar is there. So from minus 0.5 to plus 0.5 is all considered 0. So that is what x is equal to 0 in discrete. This is all there is. I am only asking for this probability. In the continuous it's minus 0.5 plus 0. Minus plus. Okay. No. Don't. Okay, now the question only from, I think even in the back you can see. I should not have done that. Okay, x more than or equal to 3 and less than or equal to 10. Okay, 2.5 to 9.5 was said, but I think retracted. 10.5 is what people are saying. Okay, 3 is included. 3 starts at 2.5. 10 is included. 10 ends at 10.5. 2.5 to 10.5. X is more than 3, less than or equal to 10. Okay, so more than 3. 4 is the first one included. So 4 starts at 3.5. 10 is included. 10 ends at 10.5. Good. 4 and 3.5 to 10. X greater than 0.
Minus 0.5.
X is greater than 0, so that means the 1 is the first one included. 1 starts at 0.5. That's it. Just think about the sign, whether I am looking at ending or starting, depending on whether I am looking at less than or greater than. And then see where it ends. The 0.5 has to come in. That's it. 0.5 has to come in. 3.5 to 9.5. Okay. Good. Okay, great. So now we know what continuity connection is. Perfect. Okay, let's see. Know that. So now you are again playing who wants to play a winner 5-star. Now the question has changed. What's the probability of getting at least 30 questions out of 40 correct with the same conditions? Each question has 2 possible choices. So I am looking at least 30. So 30 or more. And the binomial is 40n and the probability of getting the correct answer 0.5. Okay, so can I approximate it to normal? First, why? How? NP is equal to 20 and Q is also 20. So both are more than 5, so I can approximate it to normal. What would the normal distribution be? X is randomly distributed as normal 20, 10, because NP, mean is NP, so 20, variance is NPQ, 40 times 0.5 times 0.5, 10, so 20, 10. And what am I interested in? Greater than 30? Less than or equal to 40? Well, less than or equal to 40, everything 100%. I'll either get 0 correct answers or 1 or 2 or all the way up to 40 I guess. 100% area. Where did I hear the 29.5 the first time? Okay, multiple hands came up. 29.5. 29.5. There was a 29.5 here also. Here also. Just now we covered all the discrete, the continuity correction. So 30 starts at 29.5. I have to do that. Otherwise, it will give me a wrong probability. Of course, you can just go with the binomial and let it go. But that's what it is. Okay, great. Okay, then what do you do if I have to continue with the problem? What do you do? Let's go. Then first answer, let's go. What is the Z score? What is X? Huh? Oh, yeah, okay. Like I said, I am a bit slow, so step by step. So 29.5 minus 20, you are already telling me 9.5. That takes me some time to get there. So 29.5 minus 20 divided by square root of 10. Then I look up my table. Or I do my P norm, 1 minus P norm. 29.5 is the value I am interested in, comma, 20, comma, square root of 10. Or if I convert it into z-scores, I get the same thing. Whatever is the value I am interested in, the z-score that I calculate, 29.5 minus 20 divided by square root of 10, that's z-score, comma, 0, comma 1. A z distribution has a mean of 0 and a variance of 1. If I convert it into z-scores, my mean will always be 0 and the variance will always be 1. I get the same P naught. No? Okay, do it. Just try it out. Without the z-score conversion and with the z-score conversion and with the binomial directly, all of them just run. P binom, P norm. Okay. Let's solve the problem and then we will move on to the next section. So you have designed a new game, Angry Birds. And key to success is that it should not be very difficult so that people will get frustrated, and it should not be so easy that they don't get challenged also. Because if they don't get challenged, they'll get bored, they won't play much longer. If it is too difficult, then you have to seek some police protection. Because the guy who designed Flappy Birds, there was a game like that, and people were finding it very difficult to get there to some level, and he was given death threats. He had to take the game off. The original Flappy Birds game is not there on the Android store or the iStore, Apple store. Variants of it have come up, but that's what happened. He was given death threats. The people were just getting too frustrated. They couldn't solve it. Okay? So it is very important how you design the game. So if you want to design the next level, you want to understand what is the mean time people are spending and what is the variance or the standard deviation people are taking. So that if you know it's, and if you assume that it's normally distributed, you know how many percent of the people within plus minus 1 standard deviation. 68% of the people will be finishing the game within the average plus minus 1 standard deviation. 95% of the people will be finishing the game within the mean plus minus 2 standard deviations. And then plus minus 3, how many? 99.7. That's all there is in normal distribution. I have an empirical rule. If I need to use it, I calculate z-scores. I look for either the probability or the x-axis. Nothing else I can do. And within that only I have to look at this problem also. So, I have assumed that the number of minutes that a person is spending on playing the game is following a normal distribution. The probability of a player playing for less than 5 minutes is 0.0045. Probability of a player playing for less than 15 minutes is 96.41. So, very few people are finishing in less than 5 minutes. Almost everyone is finishing in less than 15 minutes. So, somewhere that is the range. What is my x-axis? What unit? What am I looking at? Time in minutes. Okay? And the probability is there. So, probabilities have been given to me now. I need to know the x-axis, the mean. Mean is what I need to find out now. So, on the x-axis, some value I have to find out. Okay? So, how do I do that? I again go to my z-score. Z-score, how do I calculate? I have not been given anything else. I have been given a probability. See, if the z-score is given, you calculate probability. Z-score is nothing but on the x-axis, the standardized values of the x-axis. I calculate probability. If the probability is given, I calculate the z-score. Q norm. This is a classic example where Q norm again is needed. Just like when Julie wanted 80% probability of finding the right height. The area under the curve was given. We wanted to find the height of the heel. Okay, so same way, I have been now given a probability of 0.0045. Probabilities are all here. 0.0045 here, right here. So my z-score is minus 2.61. That's it. Minus 2.61. So if the probability is given, I find the corresponding z-score. If the z-score is given, I find the corresponding probability. Nothing else can be done. Even if you want to do something else, there is nothing you can do. Okay? So that's about it. Now I have another probability that is given. 96.41. 96.41 here. 96.41. 1.80. So Z2 is 1.80. Now I have two Z-scores. I have two unknowns, mean and standard deviation. Two unknowns, two equations, I find them. How do I find them? Minus 2.61 for which value of x? 5 minutes. 5 minutes minus mean divided by standard deviation. 1.8 was for the 15-minute thing. That's it. I have two equations, two unknowns. My mean is 10.925 minutes with a standard deviation of 2.27 minutes. Now you tell me, 95% of the people will finish the game within what range? Plus minus 2 sigma. So 10.925 plus minus 4.54 minutes. So 6.5 to about 14 point something. That's the range. Most 95% of the people will finish. 68 is much. If I ask you 60%, then you have to go to 60% area is given to find the corresponding z-scores or the minutes. Q naught. Okay. Great. So now I have that. So that's what normal distribution along with all the continuity correction. That's what it is. I think I mentioned when I was talking about box plots that I will relate that empirical 1.5 times IQR. Why that 1.5 I will relate with normal distribution is what I said. And here is what I will talk about it briefly. This we have just seen. 68% of the data is within plus minus 1 standard deviation, 95 or whatever. Okay? 68%, 95, 99.7. But this is my box plot. Instead of vertical, I have just made it horizontal. For a perfectly symmetrical thing, median is right there in the middle, on top of mean. 25% of the data between Q1 and median, Q2 and Q3, 25% here, 25% here. Okay? So how much data in the middle? 50%. How much data to the left of Q3? So left of this Q3, this area is 75%. If I am right here, this area is 50%. To the left of this, 25%. That's what it is now. So if I am now looking at it, if I want to find this z-score here, how do I find that? I need my Q norm now. I'm looking at the x-axis value. I'm looking at Q norm. Do I know the probability? I know that. 75% of the data is less than this. So I do what I did in the previous slide. 75%. Where is that? 75. Actually, right in the middle of this. This is 0.7486, 0.7517. So somewhere in the middle of that. So 0.675. About 0.675 or something. 6745. In the next slide, if you want to get to exactly that 6745, you just have to scale it correctly. But don't worry about it. You can get exactly 6745, but you get the idea. It is somewhere between 0.6 0.65, 0.67 and 0.68. Okay, 0.675. So that is the Z-score. Being symmetric, the opposite side also. If you want to look up the other part of the table, you can look it up, or it's going to be exactly minus 0.67. It's very symmetric, so it's exactly going to be there. Okay, so now what is the IQR? 1.35 sigma. In terms of sigma, standard deviation, it's 1.35 sigma. This minus this, IQR is this minus this, 0.6745 sigma minus 0.6745 sigma. So 1.35 sigma. 1.5 times IQR, 1.5 times 1.35 sigma added to this 0.6745 sigma gives you 2.67 or 2.7 sigma. Clear? I am only doing this. Q3, I have found that it is 0.675 sigma, and I am adding 1.5 IQR to get this value, which is what our friend QT said, that is where beyond that are the outliers, is what he had said. So 1.5 IQR, I know Q3 value, I know Q1 value, I get the IQR 1.5 times, I add to this, I get 2.7 sigma. So approximately anything beyond plus minus 2.7 sigma is what is being considered as an outlier. Now, which is a fair enough thing. Many people take plus minus 3 sigma. Many people, based on their business problems, beyond 2 sigma is outlier. So it's all pretty subjective thing with respect to the business problem, etc., etc. So 2.7 is in that ballpark. So that 1.5 IQR, while it was empirical, it has some relationship to what we are doing with respect to normal distribution. I just wanted to highlight the importance of that 1.5 IQR, nothing else in this slide. And to get that exactly 0.6745 is, if you are interested, the scaling is a simple math, nothing fancy about it. Okay, good. So we are done with the normal distribution. And now you pick up speed. You must be thinking, this is already past. But no. Now is when the beauty of all of this starts coming together and we head towards our normal distribution. Towards our linear regression. Sampling distribution of means. Another distribution, but based on normal distribution. Now, from now on, everything is based on normal distribution. What does sampling distribution of means mean? These long phrases always confuse us. So, first of all, let's forget what is sampling. Distribution of means. Okay, it is some distribution of some mean. Mean of what? Samples. I take a lot of samples, I calculate their means, and I create a distribution of those means. It has a very important, this will lead us to the most elegant theorem in all of statistics. You can't find a better thing and most powerful in fact, that helps solve so many problems. That assumption sometimes, even if it doesn't meet exactly, an assumption of this really makes solving a lot of problems very convenient. So, sampling distribution of means. You can have a sampling distribution of anything. I have calculated means. You want to calculate variance? A sampling distribution of variance can be perfect. Sampling distribution of standard deviations can be perfect. Whatever. Everything can be done. Who stops? But this has a very, very important application. So we will talk about this. And I have just explained this. Sampling distribution of means is just take a sample. So if I have to again get the distribution, sampling distribution of means of the heights of people here. So I take a random sample. I take about 3 people, one from here, one from here, one from here, and I calculate the average height. I get one value from 3 people. I have to ensure that every sample that I take has the same sample size. Now I take another sample. One from here, one from here, one from here. I take another mean. I get another mean. I've already taken 6 people's data, but I have now calculated 2 means. Each sample had 3 people. Okay? So 2 means. Like that, I keep on calculating the means. A distribution of those means is what sampling distribution of means is. Why this is powerful is, this is not just powerful, it is, there is nothing more beautiful than this thing in statistics. So let's go to a demo, and nothing better. Derivations and all are boring and we don't care for them, but the best thing is see this in action. This is amazing. I want to be able to hear wow at the end of this. Otherwise, I don't get excited. So here it is. This is not some black, nothing hidden behind this thing. This is a uniform distribution. Uniform distribution means the probability density remains constant for all the values. Basically, this is what it is. Okay. So, well, there's nothing that is not so interesting. Normal, well, normal, yeah, not so interesting. Skewed, okay, yeah, skewed, big deal. We know those. The fun is when we build a custom thing. And custom, let me just go crazy with my mouse. Some buildings being created. This is the, let's say, this is the distribution of the population data. Crazy. I can't even explain this thing. This is ridiculous. Nobody can do anything with this data. If I give you this data, thank you very much. Okay? Nothing can be done. Let's say, okay, I have calculated the mean of this data. Mean is right there in the middle, blue colored. Mean is 17.21 for all these data points that I have collected. 17.21. The value of one, there is 1 or 2 data points, 2, 3, 4, 5, 6, 7, 8 has about 10 data points, whatever that number might be, the scale of y-axis, we don't care. But 17.21 is my mean. Standard deviation 8.51. Okay, so this is the red one. This is the standard deviation, 1 sigma. Okay, and then given skewness and kurtosis also. Actually, skewness is not bad, but it doesn't even mean anything. Okay, skewness and kurtosis for this data, if I show it, doesn't mean anything. Okay, so now we will do this. I will take 2 different types of samples. Let me say a sample size of 2. From this data set, I will pick 2 data points as a sample and I calculate their mean. Like that, I take multiple samples, 2 data points each. In each sample, there are only 2 data points. I calculate their averages and I will plot the distribution of those averages. In the bottom, I will do the same thing, but instead of a sample size of 2, I will take a sample size of 25. 25 data points I take from here and I calculate the average. That is one sample. I will take another sample of 25 data points from here, I calculate the average. So I have now got 2 data points for my new distribution of the means. Like that I will continue. So let's first start with 5 samples. 5 samples means, okay, 2 of my samples had, so each sample size of 2 data points in each sample. So for 2 of the samples, my average was 8. For one sample, the average was 10. 11, 12, 13, 14. One sample was 16 and one sample was 13. So total 2 plus 1, 3, 4, 5 samples. 5 means. Mean is 8, 10, 16. 8, 10, 16 and 20, 30. Whatever, 30. Okay. So that's what this thing is showing. I want you to understand what I'm plotting first. That's it. At the bottom also I am doing the same thing. It's asking for a break, I guess. At the bottom also I am doing the same thing. Here I have 2 samples with a mean of 17, 2 samples with a mean of 18, and 1 sample with a mean of 19. Okay, total 5 samples. new distribution. Skewness purposes also, but I don't care about skewness purposes. So here the mean is 14.4. Can you hear me in the back?
Yeah.
Okay. So mean is 14.4. Mahesh, practically. Mean is 14.4. Here the mean is 17.92. Standard deviation. You see there is a lot more spread here. So 9.3 is the standard deviation here. 1 is the standard deviation here. Pretty tight. That's what the standard deviation is telling me. How far is the data spread around the mean? Okay. So that's it. So now let me increase from 5 samples to 10 samples. Another 5 samples. Another 5 samples. So now I have 15 samples. The mean of these 15 means is now 16.9. Here it's 17.7. And there is some standard deviation 7.6. Standard deviation is coming down as I am adding more and more samples. 1.37. Like that. I can go on doing that, or I can do 10,000 samples in one shot. Okay? 10,000 samples. Wow. Okay. That is only first law. It's not even law enough. Okay. You see, okay, this is very small sample size. So, you see, something is happening. It's becoming symmetrical. But at this point, let's stop focusing on that. This is normal distribution. You see where we started? This has become. So the sampling distribution of the means, when the sample size is reasonable enough, is normally distributed. It doesn't matter how your population is distributed. The population may be normal, binomial, abnormal, anything. But the sampling distribution of the means will always be normally distributed, guaranteed. I think that's the wrong words. Okay. Not even now. Yeah, this is bad for this wow part of it. So this is not good. Okay, again, irrespective of how the population distribution is, the sampling distribution of means will always be normal, guaranteed. You cannot do anything. In this life, we have to live with that fact. It is going to be normal. But now, the second part of the wow, the real wow, is the mean of the population was 17.21. The mean of all sample means is 17.21. Ah, thank you. Wow. Not over. Okay, someone please calculate. I'm bad at this math. 8.59 divided by 5. Someone do that. One point 7273. Wow. The standard deviation. So now the whole thing summarized. Irrespective of how the population distribution is going to be, the sampling distribution of the means is always going to be normal. The mean of the sample means is going to be exactly equal to the population mean, and the standard deviation of the sampling distribution of means, the standard deviation of this distribution is going to be standard deviation of the population divided by the square root of the sample size. Not the number of samples. Not the number of samples. People get confused there. Not this 10,000, 15 samples we ran, but the sample size. Standard deviation of this new distribution is going to be standard deviation of population divided by square root of the sample size. Okay. what? And this, so total 2 plus 1, 3, 4, 5 samples. That is one sample. I'll take another sample of 25 data points from here. I calculate the average. So I have now got 2 data points for my new distribution of the means. Like that I will continue. So let's first start with 5 samples. 5 samples. 5 samples means, okay, 2 of my samples had, so each sample size of 2 data points in each sample. So for 2 of the samples, my average was 8. For one sample, the average was 10. 11, 12, 13, 14. One sample was 16 and one sample was 13. So total 2 plus 1, 3, 4, 5 samples. 5 means. Mean is 8, 10, 16. 8, 8, 10, 16 and 20, 30. Whatever, 30. Okay. So that's what this thing is showing. I want you to understand what I'm plotting first. That's it. At the bottom also I am doing the same thing. It's asking for a break, I guess. At the bottom also I am doing the same thing. Here I have 2 samples with a mean of 17, 2 samples with a mean of 18, and 1 sample with a mean of 19. Okay, total 5 samples. Again. And here I am calculating the corresponding mean of these 5 means. Mean and standard deviation of this new distribution. Skewness purposes also, but I don't care about skewness purposes. So here the mean is 14.4. Can you hear me in the back?
Yeah.
Okay. So mean is 14.4. Mean is 14.4. Here the mean is 17.92. Standard deviation. You see there is a lot more spread here. So 9.3 is the standard deviation here. 1 is the standard deviation here. Pretty tight. That's what the standard deviation is telling me. How far is the data spread around the mean? Okay. So that's it. So now let me increase from 5 samples to 10 samples. Another 5 samples. Another 5 samples. So now I have 15 samples. The mean of these 15 means is now 16.9. Here it's 17.7, and there is some standard deviation 7.6. Standard deviation is coming down as I am adding more and more samples. 1.37. Like that. I can go on doing that, or I can do 10,000 samples in one shot. Okay, 10,000 samples. In this life, we have to live with that fact. It is going to be normal. But now, the second part of the wow, the real wow, is the mean of the population was 17.21. The mean of all sample means is 17.21. Thank you. Wow. Not over. Okay, someone please calculate. I'm bad at this math. 8.59 divided by 5. Someone do that. $1.7273. Wow. The standard deviation. So now the whole thing summarized. Irrespective of how the population distribution is going to be, the sampling distribution of the means is always going to be normal. The mean of the sample means is going to be exactly equal to the population mean, and the standard deviation of the sampling distribution of means, the standard deviation of this distribution is going to be standard deviation of the population divided by the square root of the sample size. Not the number of samples. Not the number of samples. People get confused there. Not this 10,000, 15 samples we ran, but the sample size. Standard deviation of this new distribution is going to be standard deviation of population divided by square root of the sample size. Okay? This is what, and this, my friends, is called the central limit theorem. CLT. And we will see one example where you will just not believe me, and I don't know if I will be able to convince you, but that's how powerful this thing is, that's how things are in the statistical world. So just a third example from now, maybe before today, we'll finish that. Okay, so this is what we have seen. Okay? Sample size has to be large enough. In statistical terms, the sample size large enough means a sample size of 30. Okay, 30 numbers, but I will talk about other ways of thinking about the sample size. Okay? We will talk about that briefly in the next session. But that's what it is. Okay, so, and this being the distribution, I need to be worried about its expectation and variance, which is what we have seen. The mean of all sample means I said, what is the expectation? So, expectation of the random variable. Now, random variable is the means. Okay, the x bars, the means. The mean of all sample means is equal to the population mean. Variance of all sample means is equal to population variance divided by sample size. We looked at the standard deviation. Standard deviation is population standard deviation divided by square root of it. And what the standard deviation, now this is a completely new distribution. What is the x-axis here? Means. X-axis is not now the heights of people, not the individual values. X-axis is now the means. Other than that, it's still a normal distribution. How does it matter? To a system, to a computer, it won't even know. If I just give it a data and I don't tell it it's actually the means, I know that it's means. How does it matter? Same thing. So, nothing changes. Thinking doesn't change at all. Calculations don't change at all. But what mean here means is it's the mean of one sample. And I'm saying the mean of all sample means is equal to population mean. So here, what I really have is, let me just draw it. So what I really have almost right. Okay, so here is a little bit of skew, but that's okay. This is the best I could do so far. Okay, so now in any of these, I just is the mean. Mu, Greek letter, so it is the population mean. But this is actually the mean of sample means. But at the same point. So this is the population mean. Let's say I have a sample here, x1 bar. That is the mean of the first sample. What this is saying, and if let's say this is one standard deviation away, what it's telling me that this sample is one standard deviation away from the population mean. The sample mean. I take a sample data and I use that, and I now am inferring. So far we were only talking about descriptive statistics. We have suddenly now moved into inferential statistics. I am using a sample and I am making an inference about the population there. I don't have the population data. So all I am saying is the standard deviation tells me how far away is the population mean from the sample mean, because the x-axis is all sample means. Okay? How many standard deviations away is this sample mean away from the population mean? And so now, because I have got into the inferential statistics, I don't call it standard deviation anymore. Calculation doesn't change. It is the same concept. But now, because I am inferring, I have taken a sample mean and I am saying the population mean is going to be this much based on this. Obviously, there is an error. I cannot be perfect. I am using a sample and I am talking. That error, I am now talking in terms of the standard deviation. So, the same standard deviation, now I have changed the name. I call it standard error. It's the same standard deviation calculation, but the standard deviation of the sampling distribution of means is called the standard error. Okay, so from now on when I say standard error, don't confuse it with a new concept. Same standard deviation of which distribution? The distribution of the means. And I am calling it error because I am making an inference about the population from the sample. That's why I am calling it an error. Standard deviation, I am describing the data. Here I am not describing the data. I am making some inferences about population. So that's why I am calling it error. There is no other reason for calling it error. It's the same standard deviation. And so, the standard error or the standard deviation of the sampling distribution of the means is equal to sigma divided by square root of n. Just the relationship with the population mean. Otherwise, nothing else in this thing. It is again the same normal distribution. It has a mean, it has some standard deviation. The mean happens to be equal to the mean of the mean of the population. That's an information that I know from this theorem. Otherwise, the sampling distribution of the means has a mean and has a standard deviation like any other distribution. This mean happens to be equal to population mean. The standard deviation or standard error happens to be equal to the standard deviation of population divided by square root of n. There is a relationship between them. There is other. So, this new distribution, the sampling distribution of means, is normally distributed, always guaranteed with a mean, the same mean as the original mean of the population, comma, variance sigma square divided by n. That's the relationship. Okay? So, this is the central limit theorem, and same thing we have repeated. Okay, let's solve 2-3 quick problems and not quick, 2-3 problems, and then we will take a break. So let's start with the simplest one. So let's say the mean number of gems in a packet is 10 and the variance is 1. If you take a sample of 30 packets, not 30 individual gems, 30 packets, what is the probability that the sample mean is 8.5 gems per packet or less? Okay, problem understood? I have, what is 10? Population mean. 10 is population mean. What is 1? Population variance. I know the population mean and population variance based on a lot of historical data that has been collected. Enough number of data has been collected. I know that is what it is going to be. Now I have taken a sample of 30 packets. So what is this 30? Sample size. Beautiful. I am getting perfect answers. Sample size is 30. Okay? This is only one sample. These are not 30 samples. One sample of 30 packets. So sample size is 30, not number of samples. And I want to understand sample mean is 8.5 gems or fewer. Okay. And the moment I talk about sample means, I am now thinking sampling distribution of means. Okay. So how do I calculate this? What do I do next? Standard. Yeah, so that is no. Okay, so sigma square by n. So I have mu is equal to 10. Population variance is given. So variance of this distribution of means, sampling distribution of means, is equal to 1 divided by 30. 0.0333. Standard deviation is 1 divided by square root of 30. Population variance is 1 divided by 30. Okay, and I am interested in less than 8.5. The value that I am interested in is less than 8.5 when the mean is 10 and variance is 10. What do I do next? Z-score. Same thing, nothing else. It's the same normal distribution. The x-axis means I am interested in the mean of 8.5. How far away is it from 10? Minus 8.22 standard deviations or standard errors. Okay. What's the probability of having less than 8.5 gems per packet or less? 0. 8.22. We know within plus minus 3 sigma, 99.7% data is there. Where is 8.2 sigmas? Outside this room. Okay? And here I would advise you to visualize things, this formulae, etc. Formula also, it's only the z-score calculation, nothing more than that. Okay? But visualize, what am I seeing in this bell curve? From now on, I always will talk about this. I just do this and I do this mean. That's all I know how to draw. I draw the axis, I draw the bell curve, and I draw the midpoint on that. And then I try to see where this problem, data, whatever is there, what fits and what am I interested in finding. That's all there is. So here I am trying to visualize. I don't know what the population distribution is. I just drawn it like this. I would have drawn it like this. I don't even know. I don't even care because central limit theorem tells me that however the population distribution is, if I take enough number of samples of a good enough sample size, 30 is a good enough sample size there, then the sampling distribution of the means is always going to be normally distributed, guaranteed. Okay, so I don't even care about this. However, you have given me some information about the population. The mean of the population is 10, so mean of all sample means is going to be 10, guaranteed. The standard deviation of the population is given. So the standard deviation of the sampling distribution of the means, which is nothing but standard error of the mean, is 0.1825. That is one standard deviation. 1 divided by square root of 30. That should be the value. Now, so if that is the case, one standard deviation is here. 10 minus 0.1825. 3 standard deviations, where will that be? 0.55. 10 minus 0.55. So this value here is about 9.45. This is 10. 9.8, 9.6 something, 6.3 or something, 9.4 here. See that? 1 sigma, 2 sigma, 3 sigma. I'm only doing that. No? Not here? Clear? Okay? So 3 sigma, if 1 sigma is 0.18, 3 sigma is about. So in a bell curve, I always try to see the limits of the bell curve. Where does the bell curve end? Pretty much plus minus 3 sigma limits. That way you will have a picture in your mind of how this normal distribution is. There is a mean and then there is some bell, but the bell ends at plus minus 3 sigma. Okay? So I'm just to get a visual picture of that. Nothing to do for any of my calculations. Just to get a visual picture. So 9.45 is here. I am interested in 8.5. If 10 is here, 9.4 is here, so 0.6. Then 8.8 is here, 8.5 is somewhere here. There is no data possible there. So the probability that intuitively it might sound very odd. So on an average there are 10 gems per packet. The probability of 8.5 or less, we might think, well, it should be possible. I mean, 8.5 is not far away from 10. But I'm not asking for an individual packet. I'm asking for a mean of 30 packets. When I take 30 packets, some might have 7 gems only, some might have 12 gems in there, some 8.5, 9, 10, whatever. All of them. An average of 30 packets will not end up at 8.5 gems or less. I mean, every packet should be then having 8, 9, 7, 9.5, like that. When the population average is 10, you must be really unlucky to get a sample that is all outliers. Okay, then you will get that. And if you get that, you will get wrong conclusions. Okay, so this is how you visualize and make a decision. Yes.
So what is the good sample size?
30. I'll talk about more about sample size later, but as of now, 30.
And what about sampling? Like
Random.
and how many samplings are a good practice? How many times do you need to sample?
Okay, that's an even better question. Well, theoretically, I just did a simulation where I could do 10,000. In real life, you will be lucky to have one sample. And that's where the beauty of simple limit theorem will be. You don't have this distribution. This distribution is only in your head. This is never a real distribution. But you know that if you were able to take that many samples, it will be a normal distribution. What you normally will end up with is one data point in this distribution. And from that you will be making inferences about population. That's the beauty. The next couple of examples later, I'll get to that point itself. Okay? There could be some situations where you can do many simulations. You can just generate data and simulate data. There you can do many data sets like that. But in general, most of the real life that you will see, you will never be building this distribution. You will never have data for that distribution. You just know what that distribution would be like, and you will have one data point in that distribution. We will see the power of central limit theorem in making inferences about the population using that one data point. And without knowing anything also. So we'll come to that. This is the first easy part. Real problems. I mean, people can know the population mean and standard deviation. They may not know the distribution, but I don't even care. Population mean and standard deviation may be known from historical thing. Now I have taken a sample, and if I want to make inferences, I can do it. This is straightforward. We will get to more and more real world situation in a couple of examples. But first to understand what we are doing with the sample distribution of means. Solve another problem. The Aluminum Association of America reports that the average American household uses 56.8 pounds of aluminium in a year. Okay? Now, a random sample of 51 households has been taken. Sample size is 51. And for 1 year, they saw how much of aluminium was being used by these houses. Let's say the population standard deviation is 12.3 what is the probability that the sample mean will be more than 60 pounds? Okay. Most of the time when we read a question with so much of English there, we are already lost. What are we looking for? So, in our childhood, teachers should have taught us, no? When you are given a problem, write given, and then thought, and then you write, and then step by step, and so you have to write all that. Then things become clearer. There was a reason, now I understand why they said that, because if I read this is only one paragraph. Sometimes the business problem is one page and I have no idea where I am. Okay, so good. So here, first of all, what has been given to me, that the mean of the population is 56.8 and the standard deviation is 12.3. That's again given to me. Population data is given to me somehow. I want to understand. So mean is 56.8. So I know this mean is also going to be 56.8. I want to understand what is the probability that the sample mean will be more than 60. So I'm interested in that area. I'm still calculating the area or the x-axis value. Nothing different. Okay. It's just that the x-axis is now means of many samples. So here, population mean given, this given, sample size is given. This is what I'm interested in, and I do my Excel. This is the thing, or in R, I do 1 minus P norm, and in P norm, I'm interested in the value of 60, comma 56.8, comma square root, no, so 12.3 divided by square root of, okay, here I have written that, square root of 51. That is the standard deviation of this new distribution, standard error. And I get this value, 3.16. Same thing, whatever we did for Julie, we are doing exactly the same thing. No change at all. No change at all. Okay. The x-axis values and the standard deviation, mean standard deviation. So you may want to practice for various values. Instead of 50, 60, you try 58, between 56 and 57, less than 50, all those things. If you have to get between some numbers, what do you do? Let's say 56 and 57. The P norm will always give you the area to the left of it. So P norm for 57, if you get all of this, then you get 56, you get all of this, subtract those two. Okay. Great. Okay, this is from this one and the next one from Khan Academy, and that will complete the sample distribution. So let's say an average male drinks 2 liters water per day when active outdoors, and there is a team of people you are taking, 50 men, and because you say on an average they drink 2 liters per day, 50 people will drink 100 liters. But well, we also know that there is some variance. Let me be safe. Let me calculate it, take 110 liters. Now the question is, what is the probability that you will still run out? That's what I want to understand. I can take 150 liters. Probably I will never run out. But what's the use in carrying so much more additional weight? I want to be perfect. No one should go thirsty, and I should not be carrying too much weight. I have to calculate that. And I have some information about the population. How do I do that? So, now the x-axis is liters per person. Okay? An average male drinks 2 liters of water per day. So, liters per person. Here 110 liters have been given, but that is for 50. So, when will I run out? If on an average people drink more than 2.2, 110 divided by 50. On an average, if this sample drinks 2.2 liters per day or more, then I will run out. What is the probability? It is 2.2 or more. What is that probability is what I want to understand. So I have everything. I have 2.2 is the value I am interested in. 2 is the mean. The z-score I get is 2.02. 2.02. Okay? So, and P norm will give me 97.83. So, 1 minus P norm, 2.17%. So, there is 2.17% probability that you will still run out of water, even if you are carrying 110 liters. The mean is 2. What's the probability? More than 2.2. That's it. 1 minus P norm. You need to know the standard deviation of this distribution, which is standard deviation of population divided by square root of sample size. Yes.
How did you get that 0.49? Can you say that once
Sigma square I have done actually. So the standard, I'm calculating variance there. Okay. Variance of this distribution is variance of population divided by the sample size. I have given standard deviation. I could have just done 0.7 divided by square root of 50. I just did extra work. First got the variance and then went back to standard deviation. I could just have done standard deviation. This is equal to 0.7 divided by square root of 50. Okay, so yeah. It's been a long time since we covered confusion matrix. This is something to confuse. Okay. Fine. And then this is where all the power of central limit theorem is. Not in eating apples. That too. So now this is reality. This is what most of the time reality will be. You have a farm where you have 2 lakh apples. You want to know what is the, till now I was giving you population mean and standard deviation. Now I have 2 lakh apples. I have no clue about them. I want to understand what is the mean weight of those 2 lakh apples. What do? I cannot. If I can calculate all 2 lakh, fine. Then I don't need inferential statistics. If you have information about the population, never use a sample to again infer about the population. Why do you want to do that when you can describe the data? Why do you want to infer and have the possibility of an error when you can actually describe the actual thing? So here, now, I don't know anything about the population. I have a sample. I took a sample of 36 samples, keeping in mind sample size of 30 or more is statistically good. Okay? When it is less, we will come to that tomorrow. When it is less than 30, what happens? But as of now, 36 good sample size. Okay? Now, those 36 samples I can weigh. I weighed them and I got a mean of 112 grams for these 36 samples and a standard deviation of 40 grams for these 36 samples. The standard deviation of this one sample, it is neither the standard deviation of the population nor the standard deviation of the sampling distribution of means. It is the standard deviation of these 36 samples. Okay. Now, with that, I want to understand what is the probability that the mean weight of all 2 lakh apples will be between some 2 numbers. Here, for convenience, I have taken plus minus 12 grams. You can take plus 50 grams minus 30 grams. What are these grams? These are the x-axis values. I have to calculate corresponding z-scores for them. That's it. Nothing fancy. I can have any number. Just for ease, a symmetric thing is what I am asking for. Okay. So this is what I want to find out. So let's see. Let's try to draw. This is my population distribution. I don't know the mean. I don't know standard deviation. Nothing known about the population. But I do know that if I were to take many samples, the distribution of the means of all those samples will be guaranteed normal distribution. That I know. However, having said that, I again don't have that many samples. I have one sample mean, 112 grams. In this distribution, I have one data point. From that data point, I have to talk about the population mean. Whether it is plus minus 12 grams. This is what the reality is. Okay? So, and I do know the mean of all these sample means is going to be population mean, but I don't know what that number is. I know the standard deviation of the mean of the population. That's something I'm trying to find out. I don't know that. The standard deviation of all these sampling means will be equal to standard deviation of population divided by square root of sample size. Sigma divided by 6. Of course, I don't know sigma also. Okay? But this is my situation. At this time, I have to now start thinking what do I do. What am I trying to find out? I'm trying to find out if this population mean is within plus minus 12 grams of the sample mean. I actually don't even know where my sample mean is in this distribution. I know 112 grams on this x-axis. Is this here? Is this here? Is this right here? Is this here? Is this here? Where is that? I don't know that also. Okay? This is the beauty of the whole thing. I just don't know anything. Okay? Ignorance is bliss. Okay. So, I am trying to find out that this population mean is within plus minus 12 grams of the sample mean, which is somewhere here. Now, I am looking at this distribution, this distribution. How can I really find something from two different places? So, let me play with English a little bit. If the population mean is within plus minus 12 grams of the sample mean, it means the same thing as that the sample mean is within plus minus 12 grams of the population mean. I have not done anything, but I have done a very important. Is the sample mean, that 112 grams, is that within plus minus 12 grams of the population mean? The population mean is going to be this value here. Okay? What is the probability of the sample mean being within plus minus 12 grams of the population mean? Okay. Now I am talking only this distribution. I don't care about this. Is the population mean within plus minus 12 grams? You have to create multiple distributions. You have to say, is the population mean within 10 grams? Is the population mean within 9 grams, 8 grams? Multiple distributions, and you have to check. But by twisting the statement, is the sample mean within plus minus 12 grams of the population mean? The population mean is here. Is the sample within plus minus 12 grams of that? I know the sample is 112 grams. That's what I need to find out. So let's do it. Okay, this is what I've written there. But even then, so now some part of the problem is clear in terms of English. I'm looking at this distribution. I'm trying to see. I have a sample with 112 grams. I want to find out whether that 112 grams is within plus minus 12 grams of this guy. That's what I'm trying to find out. But then I still don't know anything else. At this point, I have to make assumptions. And a very good assumption to make is, when I don't know anything else, I'm trying to find out the mean. So I can't make assumptions about the mean. But I can make an assumption that if the sample is representative of the population, then the sample standard deviation should be close enough to the population standard deviation. That is an assumption I will make, and that is called a point estimate. So I will replace the sigma, the population standard deviation, with the sample standard deviation. Sample standard deviation was 40 grams. I cannot say the standard deviation of the means is 40 grams. The standard deviation of only one sample. But if this sample is really representative of the population, then it should not be way off. Approximately it will be there. And if you don't want to believe me, let me just show you some Excel numbers I had played with some time back. This one, not this one. Anyway, okay. The font visible in the back?
Yeah.
Okay. So what I did is, let me remember what I did. I think I took 5,000. Okay. with an average of, I gave the average of 500 and the standard deviation of 100 or something. So approximately that came out to be this much. Average of 498 and standard deviation of 101. That was this data. Now, this is the entire population, 5,000 data points. Okay. I know this, but in the Apple's case, I don't know that. So, what I did is, I randomly from this data set, I selected some data here, and from there, I took a sample size of 10, 20, 100, 1000, etc. So, I have randomly picked about 10 data points from here. Because this keeps on changing, I think, so I copied and pasted as values from here, I guess. Okay. So, I randomly took some data points, 10 data points from here, and I calculated their average and standard deviation. See, 101.17, 101.9. This is luck. This can be luck. I mean, 10 data points is very small. I could be off also. The 20 data points, you see, it's a little bit off. 82.25, 100 data points, 1000 data points, you see, now they won't change. They are pretty close. The larger the data size, closer it is. And 30 is considered a reasonable number. So, that is not a very bad assumption to make. That the sample, with the strong assumption that the sample is representative of the population. Now, if your sample really is not representing population, sorry, you can't do anything. You will make a mistake, but that's where the probabilities come into play. Okay? So, the sample is a representative of the population. That's where you have to be very carefully collecting the apples. If you have a large farm, you have to ensure that if the soil is different in different parts of your thing, whatever is affecting or the sunlight is not equally falling on all of them, or taking apples from the top of the tree, from the middle of the tree, bottom of the tree, understand as much about the population as possible and then take a random sample of those 30 apples, 36 apples. Then you have, it is a fair assumption to make that the standard deviation will be fairly close to the standard deviation of the entire population. Okay, so, and that assumption is what we make. Okay. And with that assumption, now I have a standard deviation of the population, which means the standard deviation of the sampling distribution of means, or the standard error, is sigma divided by 6 is what we have calculated, 6.67. Now my problem is resolved. What am I interested in? Is the population mean within plus minus 12 grams of the sample mean, or is the sample mean within plus minus 12 grams of the population mean? If 6.67 grams is one standard deviation, how much is 12 grams? 12 divided by 6.67, or 1.8. Now that is the z-score. Within plus minus 1.8 standard deviations, I am trying to find out, is the sample mean within plus minus 1.8 standard deviations of the population, or is the population mean within plus minus 12 grams of the standard deviation, or plus minus 1.8 standard deviations of the population? A sample. 100 to 124 grams is what we were looking at. That's what I want to find out. That 100 to 124 is plus minus 1.8. Now that we know that, you do a 1.8 here, 96.41. 96.41 is what? Less than plus 1.8 standard deviation. Let me draw that. Actually, this, okay, another one. This is, you watch me, what am I doing? I am always good. No, that I cannot do. I just end up doing these things. Okay, way off. But now I am saying, is the sample mean within plus 1.8 C and minus 1.8 C? So I need, so when I look up that 96.41, what I get is this is 96.41. And so I subtract this part from there to get this probability. This is the area. So I can look up minus 1.8 and get the area and subtract this area from that one. Or else it is from 96.41, I am pretty, it's easy. I know this is 50% of the area to the left of 0. So 96.41 minus 50, 46.41. So this is 46.41, so this will also be 46.41, 92.81. Okay. Or else you just look up minus 1.8 as well. Or the P norm. P norm corresponding to 1.8, P norm corresponding to minus 1.8. And you get the answer as 92.82%. This is the power. You are now saying that there is a 92.82% probability that the population, the mean weight of the all 2 lakh apples is going to be between 100 to 124 grams by using one sample of 36 apples. There is that 7.18% chance that it will be outside of that. Well, with 36 apples, if you are able to make such a big inference, then that's a great thing. You want a better thing, you just take all the 2 lakh apples and pay them. This is great. Very powerful. Wow. Okay, let's take a deep break and then I will have another problem with sampling distribution and without the sampling distribution, how to see them again.